Hi everyone, my name is Amy Mendenhall and I am a technical marketing specialist at GenScript. I received my PhD from the University of Michigan in neuroscience, where my thesis focused on the role of beta-1 integrin, integrin-linked kinase, and caveolin-1 in neuroblastoma cancer. I then worked as a technical support scientist at Ingenuity Systems and then at System Biosciences, where I helped new customers learn how to use their products and services. During today's webinar, first I will give an overview of the anti-cancer immunity cycle and describe key checkpoints that are useful for anti-cancer therapies. Then I will introduce GenScript's new line of immune checkpoint stable cell lines. I will show you how these cell lines were developed and tested, and also present some ideas for applications of the immune checkpoint cell lines. I am joined today by Dr. Zhang, PhD, Lead Product Development Scientist. Dr. Zhang led the development of the immune checkpoint cell lines, and he will be available for questions at the end of the presentation. To ensure the sound quality, all attendees are muted. Please feel free to type in your questions in the chat box in the lower right corner of your screen throughout the talk. Dr. Zhang and I will address your questions together at the end of the presentation. The cancer immunity cycle describes a process of how one's own immune system can protect the body against cancer. When performing optimally, the cycle is self-sustaining. With subsequent revolutions of the cycle, the breadth and depth of the immune response can be increased. Here, in steps 1 through 3, the anti-cancer immunity cycle is initiated and propagated. Oncogenesis leads to the expression of neoantigens that can be captured by dendritic cells. Dendritic cells can then present antigens to T cells, priming and activating the cytotoxic T cells to attack the cancer cells. In steps 4 and 5, the tumor is accessed. Activated T cells travel to the tumor and infiltrate the tumor microenvironment. Then, in steps 6 and 7, cancer cell recognition and initiation of cytotoxicity occurs. Activated T cells can recognize and kill target cancer cells. The dying cancer cells then release additional cancer antigens, propagating the cancer immunity cycle. In the cancer immunity cycle, several known factors can act as stimulatory or inhibitory signals at each step. This slide displays some of the known stimulatory and inhibitory signals in green lettering versus red, respectively. So here at each of the steps, what you can see is there's a list of molecules that are either stimulatory, shown here in red, or inhibitory, shown in green. Each step in the cancer immunity cycle represents a point at which a given cancer therapy could be implemented. For example, at step 1, release of the cancer cell antigens, traditional therapies such as chemotherapy, radiation therapy, and targeted therapies are normally used. Here at step 2, cancer antigen presentation, vaccines, interferon alpha, GM-CSF, and anti-CD40 antibodies, which act as agonists, and TLR agonists have all been used for successful cancer therapies. At step 3, priming and presentation, agents that can be used for cancer therapies include anti-CTLA4 and these other molecules that are shown here. At steps 4 and 5, this involves trafficking of T cells to tumors, and that involves transit through the blood vessels and infiltration of T cells into the tumors. So anti-VEGF has been used as an anti-cancer therapy. At step 6, recognition of cancer cells by T cells, CARs have been used for anti-cancer therapy. Steps 1 through 3 of the cancer immunity cycle are excellent targets for effective cancer therapies. If you can boost the reaction of the T cell signaling and activation, then the body can help fight the cancer on its own. In fact, many cancers protect themselves from the immune system by inhibiting the T cell signal. So this is a little infographic that shows a T cell expressing many of the proteins it normally does, such as PD-1, T cell receptors, CTLA-4, and then how the tumor cell would normally interact with these T cells. Here's a dendritic cell also interacting with these T cells. So these molecules all here represent potential targets for cancer therapies. Immune checkpoints are molecules in the immune system that either turn up a signal, which are called activating, or turn down a signal, known as inhibitors. This infographic shows many of the available T cell receptor interactions that could serve as targets for anti-cancer therapies. So this shows you there are just very many molecules that could be used. And then here's one example of, here on the left-hand side, activating receptors such as CD28, OX40, GITR, and here on the right-hand side, inhibitory receptors such as CTLA4, PD-1, etc. These would all affect cancer immunity. So GenScript has recently developed several stable cell lines expressing immune checkpoint molecules. These can be used for immunogens for immune checkpoint antibody generation, tools for high throughput antibody screenings, cell-based immune checkpoint bioassays, in vitro anti-cancer drug screening and profiling, and tools for establishing in vivo animal models for immune checkpoint studies. So how did GenScript build and characterize these cell lines? Well, first of all, they started with either Chinese hamster ovary, which are called CHO cells, or human embryonic kidney HEC293 cells. These cells were transduced with lentiviral particles that express the immune checkpoint gene of interest, along with G418 resistance. The immune checkpoint gene of interest is randomly and stably integrated into the host cell genome for permanent expression of the gene. This is the property of lentiviral transduction. Cells can be then passaged or frozen down without a decrease in expression of the immune checkpoint proteins. All of the cell lines, the CHO and the HEC293s, have a high expression of the surface proteins. So here we show a listing of some of the available immune checkpoint cell lines. The way that this is listed is the type of cell that it's in is listed first. So here are CHOK1 cells, and then the protein that is expressed is shown second, so human PD-1. You can see there's a nice variety of immune checkpoint stable cell lines available. The immune checkpoint stable cell lines mentioned here are all GenScript catalog products that are available off the shelf. This is nice because you don't have to wait for a custom cell line to be built in order for you to start using it. There's a high cell surface expression of the subclones, and this is validated by FACS in the intact cells. The stability of the target protein expression is at least 15 passages in culture. And there's about over 90% viability when the cells are thawed from liquid nitrogen. And all of the cell lines are certified mycoplasma negative. These data show that expression of the surface markers, after creating the immune checkpoint cell lines, each was validated for the cell surface markers it expresses. This FACS analysis of the human PD-1 expression in HEC293 and CHO cells shows that there is a dose-dependent correlation of expression of PD-1 when cells are treated with a stimulator drug. Furthermore, a FACS-based binding assay here shows a similar result. So you can see a nice expression of the human PD-1 in these CHO cells and that it responds appropriately to the drug. These data here show the expression of the surface markers is enhanced versus a control for one of the proteins being expressed. So here in the red trace, we're looking at CHOK1 cells. The dark red is showing expression of B7H4, and the pink or the light red down here is showing the control cells. And so what you can see is that there is a higher level of the B7H4 expression in the stable expressing cells versus the control cells here. The immune checkpoint stable cell lines can be used for several applications. Today we will look at how they can be used as immunogens for immune checkpoint antibody generation, tools for high throughput antibody screenings, and cell-based immune checkpoint bioassays. Let's start by looking at the immune checkpoint stable cell lines as immunogens. So this slide is showing a comparison of different ways of creating antibodies. And I'm going to start actually over here on the right-hand side of this table, where you can start with a DNA plasmid that is encoding the gene to create a protein. And this can be used as a way of producing an immunogen for antibody production. It's nice because it allows for native conformation of the protein. The protein folds within the cell, whatever cell it's being produced in, and then you should be able to get a nice antibody production. However, one of the limitations is that there's a low protein expression here. There can be low protein expression, and also this could lead to a low antibody titer. This method is also quite expensive. You can also start with a synthetic protein or a purified protein to be used as an immunogen for antibody production. This is a good way. It provides for high throughput screening compatibility. It gives a wide range of epitopes that are available. However, purified proteins, especially from bacterial cells, might lack the native conformation, and they might be non-functional proteins. This could make it more difficult to create an immunogen or an antibody for a native state immunogen. It's also a more expensive way of creating antibodies. Another way of creating antibodies, of course, is to use a synthetic peptide. This is great for HT screening compatibility. However, the peptides are normally linear and they're non-functional. The antibodies are then raised against a linear epitope instead of the native conformation of the protein, and it's typically not recommended for therapeutic antibody generation. It is a cost-effective method, though, of creating an antibody. So the one I wanted to focus on today is using the stable cell lines that express the target as the immunogen for antibody production. It has many advantages. First of all, it starts with the native conformation of the protein. It's also compatible for high throughput screening. The antibodies are raised against the conformational epitopes, and so not just the linear epitopes. And it can also be used for therapeutic antibody generation. The one disadvantage is that you need to have a high expression of the protein, at least a 1 log shift in flow cytometry measurement. However, it is a very cost-effective way. And so you could use the GenScript stable immune checkpoint cell lines. They're already generated. They already have a high expression of the immunogen. And so you could use these for your own antibody production. We've looked at using the immune checkpoint stable cell lines as immunogens. So now let's focus on using them as tools for high throughput antibody screenings. High throughput screening can be performed using either ELISAs or FACS. These assays can measure binding, quantitation, and competition. Peptides, proteins, and cell lines can all be used in ELISA studies for antibody screening. However, the cell-based FACS antibody screening leads to the highest hits against the native conformation of the protein. So here's one example of a high throughput screen. It's shown here, and in this case they use the CHO human PD1 stable cell line. 2 hybridoma fusions were formed from 2 immunized mice, and they got 843 hits identified in the primary ELISA study. In a total of, they used 65 96-well plates of hybridoma supernanes, and they were screened against the PD1 protein antigen. Of those 843 screened, 86, so about 10% of the hits also blocked the binding between PD-1 and its ligand, which is called PD-L1, in the secondary ELISA study. And then only 26 out of those 86 parental clones bound to PD-1 expression on the human PD-1 stable cell line FACS study. This is some data of FACS trace here. In black is showing the control cells, and in red the human PD-1 stable cell line. And so we're looking at this one here. So after identifying the 26 parental clones, the clones were subcloned and subjected to further characterization. They made 53 subclones that blocked the PD-1 ligand binding to PD-1 that was expressed in the CHO human PD-1 stable cell line. This is again using FACS. And 28 out of the 53 subclones were tested for their functional activities in a mixed lymphocyte reaction. So in addition to studying, the binding, you can also then study the function of the antibodies that you created. And so here's a FACS study showing the representative positive subclones by FACS. And then here is the data from the mixed lymphocyte reaction. IL-2 production indicates a stimulation of T cells. Lastly, let's look at some of the cell-based assays used with immune checkpoint stable cell lines. So CTLA-4 is a member of the immunoglobulin superfamily that is expressed on the surface of helper T cells, and it transmits an inhibitory signal to T cells. CTLA-4 is similar to the T cell co-stimulatory protein CD28, which on this slide is going to be shown as a blue oval. And both of the molecules, CTLA-4 and CD28, will bind to CD80, which is present on antigen-presenting cells. Also, CTLA-4 transmits an inhibitory signal to T cells. Also on this slide, you see IL-2. IL-2 is an indicator for T cell and Jurkat cell activation. In this study, we're using Jurkat cells because they are a cell line that resembles T cells. And the more Jurkat cell activation there is, the more IL-2 is in the system. So in here, in this study, Jurkat cells were activated when CD80 expressing CHO cells were co-cultured with CD28 expressing Jurkat cells. So it's a co-culture. The CD80 CHO cell line was the one that was used. This is GenScript's cell line. And these are cultured together. And when you measure the amount of IL-2, you can see an increase in IL-2, indicating stimulation of the Jurkat cells. When CTLA-4 protein was added into the CHO cell co-culture, the CTLA-4 competed with the CD28 abilities to bind to CD80, and less Jurkat cells were activated. So CTLA-4 comes in, it blocks binding here, and then when you measure IL-2, you see a decrease, and this indicates inhibition of the Jurkat cells. Lastly, when a CTLA-4 protein and an antibody to the CTLA-4 were added to this CHO cell, CD80 cell, Jurkat cell co-culture system, the anti-CTLA-4 blocked the binding between CTLA-4 and CD80. So it allows the Jurkat cells and the CHO cells, again, to bind together and cause a stimulation and showing an increase in IL-2 again. So this is one example of a cell-based assay that used GenScript's checkpoint cell line. This slide then shows some more data from the cell-based anti-CTLA-4 activity assay. It's showing EC50 curves of two independent screens with a test drug here. The test drug is shown in black, green, and blue, and then the control is human IgG1. And so as you can see, when you add in the test drugs that bind against the CD80 expressing CHO cells, you see an increase in the amount of IL-2 produced. GenScript also has other stable cell lines available for purchase. Especially they have some CHO and HEC293 cells expressing G protein coupled receptors. These can also be used similarly for assay development, screening, or antibody production. And GenScript can also create stable cell lines for you. So now I'm going to open the lines for questions. And Dr. Zhang is also going to join us now in case we have some questions. If you have a question, please feel free to type it into the question box, which is at the bottom right of your screen. And as the questions come in, I will start to let you know what they are and then answer them. So far I don't see any questions. You can feel free to ask any questions about how the technology works. Here we go. So here, I wonder whether immune checkpoint protein expressing cell lines can be used for quantifying antibodies in serum in a non-clinical primate study. Oh, that's a really good question. And Dr. Zhang, can you please help with this question?
I don't know. So which antibody you use? So if I think possibly it will create lots of the background for the because they have lots of IgG in the serum. So I think possibly it will be difficult to use the serum to identify the quantify the antibody in serum.
Okay. So you think this one might be difficult, or it might take some extra?
I think it might be difficult.
Yeah. Okay. So in this case, Dr. Zhang thinks that this particular use case might be a little bit difficult to do. Maybe it could happen with some pilot studies or some extra planning ahead, but we haven't really tested that here. Any other questions? Okay, so I wanted to thank everybody for attending today's webinar. If you do think of any questions after we've ended the session, please feel free to check the GenScript website and send a question to either your sales representative or also their tech support team there. We can answer any questions if you think of them later. And if you have any sales or pricing questions, again, you can also contact your GenScript sales representative. And just thank you for coming. I hope you enjoyed the talk.